Testing 1, 2, 3. Can you hear me?
Okay, where do you want me to start?
Well, I work with beef cattle, and beef cattle generate manure every day. Our focus here is trying to take what cattle excrete and actually make methane or biogas from that manure. And the reason to do that is because methane then can be burned for energy. So cattle normally produce methane in their rumen system, which is a bad thing, but if we can get them to produce it in the manure and capture it as energy, it's a good thing. What's unique or new about our system is that this is integrated into a larger, what we're calling a biorefinery concept, where cattle are important to the system, manure digestion is important to the system, growing algae off of manure is important to the system, and producing ethanol and producing distillers grains to feed back to the cattle. So it's kind of a loop, if you will, where we're recycling nutrients through lots of different important ag commodities. And we believe beef cattle are an important component of that, primarily because beef cattle are important to the state of Nebraska. And so if we can figure out ways that they fit in to generate energy for our state, that's only a plus.
Well, the project I'm working on is trying to identify small chemical compounds that will cause algae, which are photosynthetic organisms, to produce oil from carbon dioxide in the air. The problem is that we don't really understand algae very well, and we don't understand what causes them to produce a lot of oil. And most of the methods that we have right now cause them to stop growing, and they lose their green color, so they aren't undergoing photosynthesis to capture the CO2 to make these hydrocarbons. Since we don't understand the biology and genetics, I'm using an approach that's called chemical genetics. And so we have libraries of small compounds, and we use these libraries of compounds to test our algae. And the way we do it is we take a plate that's as small as this, and it has wells in it, 384 wells, and so we put in little amounts of algae in each one, and we put in a different chemical in each plate. And then we put it under lights, and we let them grow. And then we look at those and we ask, did they stay green? Did they increase in number? And are they producing a lot of oil? We then scale up a little bit to see if we can reproduce that result. And eventually we'll try to get up to hundreds of gallons of algae to be able to produce oil in response to this chemical.
Our project is related to variable rate irrigation systems, and what we're looking to do is improve irrigation use efficiency. Variable rate irrigation systems basically allow us to move water around the field. So instead of applying a fixed rate, maybe 1 inch every revolution, it gives us the ability to change those rates. For instance, if we want to put water on a more productive area of the field, maybe reduce water in other areas, those are some of the different options we have for that. What we're looking to do is control the speed of the pivot, and the second portion is the use of variable frequency drives on our pumping systems so that we can actually increase or decrease our pump energy needs to deliver that water to the pivot system. But the problem is there's just not a lot of good information out there right now on how people can actually evaluate those systems to find out if it's what would meet their operational needs. So what we're trying to do is provide producers and potential adopters with more information about whether or not they'll see benefit from using this technology, whether that is in more efficient use of water or potential energy reduction for their irrigation system.
We use energy almost everything in the world, and supplying water to crops is one of the basic uses in Nebraska. And so water not pumped is energy saved. So the key there is with irrigation scheduling, you should be putting on water and adjust the right time and amount. So therefore you'll be very efficient in applying water only when the crop needs it and in the amount the crop needs. In order to do irrigation scheduling, you need to have an estimate of the daily crop water use. But that requires daily weather inputs of solar radiation, wind speed, temperature, and humidity. And in the past, when producers had to get those, they had to call up every day to get that information. And so it occurred to me that maybe we could do this a lot better by setting up a website. And so that's what we did. We developed something called UNL Soil Water that producers can access free of charge. And it updates the weather data for them automatically. All they have to do is enter their soil type, their planting date, cultivar maturity. And otherwise, it's pretty easy for them to find out when to irrigate their soybeans, and efficiently and just at the right time. And we're going on to try to improve it by making it a corn soil water project, in which producers then can use their smartphones and to access what their status is on every field each day. Irrigation scheduling was manual drudgery, even with a computer, but with this website, easy as 1, 2, 3.
So my lab is studying graphene, and graphene is a new two-dimensional material which is made of carbon atoms. So this model actually shows you what graphene is. So you have carbon atoms in a hexagonal lattice. And although it looks like a very simple material, it has lots of unique properties. It's mechanically stable, it's electrically conductive, it's flexible, and it has a very high surface area which could be utilized for the energy storage. Because if you look at this model, you could see that actually all carbon atoms in this material are the surface atoms. So basically you have one surface here and another surface here. So which means if you want to store the electrical charge, both surfaces are available. And this would benefit all applications where you use batteries. Since graphene was discovered very recently, a lot of research has to be done on how to actually take advantage of those great properties. And that's what my lab is working on. So we're trying to synthesize graphene by new methods. We're trying to functionalize it with proper chemistries, and we're trying to build prototypes of supercapacitors. And this is something which became possible because of the support of NPPD.